screen?
Okay.
Yes, so we don't have the board today. I will, let's see what I want to do. I want actually to do this. Do this. So you can all see my screen.
Yes.
Okay, so let's start. So our lecture will be online today. Let's see. I am. So this is our lecture 13. And the goal today, I want to talk to you a little bit about differentiability. Of functions, okay? After the class today, I will give you some notes and you can follow up with the notes. You can read about it. And I guess you are due homework to me today. You can deliver to me by the end of the day. Okay. So our starting point today here for this discussion is the fundamental theorem of calculus. That is, if I have a function little f, which is continuous on a certain interval ab, and I let function big F of x being the integral from a to x of little f. Okay, so if I integrate a function, you know that then this big F is differentiable everywhere, and the derivative of this function big F, no, maybe I should write this f prime of x, which is the derivative of the integral. It's just the function that it's inside, so little f of x. Okay, so but also you have this thing, that the integral from a to b of fy dy is the integral from a to b of this f prime of y dy. And this is f of b minus f of a. Mm-hmm. So what I just wrote here, it's the fundamental theorem of calculus written in two different ways. So the fundamental theorem of calculus, you should just understand it as the statement that derivative and integral, differentiation and integration are opposite operations. You know, they are somehow like addition and subtraction, or multiplication and division. So integration and differentiation are, you know, inverse operations. So the first thing here, so this number one here says that the derivative of the integral is the original function. And the number two here essentially says that the integral of the derivative is also the original function. You know? But here I started with the function little f that was continuous on the interval ab. Then I took the integral of this guy. So this function big F is differentiable everywhere. And at every point, big F prime of x is little f of x. Okay. Now, I want to understand, so our goal today is to understand how this is still true, and I put true here in quotes, because we have to understand what it means. How this is still true under, less regularity assumptions. So this would be the goal of the class today, to talk about differentiability, to talk about the fundamental theorem of calculus. In the sense, okay, so let's go back to this situation that I just described. So you have this function big F of x being the integral from a to x of a function f of y dy. Okay, and you wanted to understand if this function is differentiable. Okay, well, the definition of differentiability, you have to take the difference quotients, right? So you have to consider quotients like f of x plus h minus f of x and divided by h. So if you put this in the integral, what this will be is just the integral of 1 over h. And then you will take the integral from a to x plus h minus the integral from a to x. So what's going to be left is just 1 over h, the integral of x up to x plus h. Okay. Look at what I have now on this right-hand side here. Okay. So I want to understand this as h goes to 0. Okay. So as h goes to 0, the fundamental theorem of calculus tells me that if your function little f is continuous, then this will converge to the value of f at x. Well, this is no surprise, because what you are doing here, you are just taking an average of this function, right? You're just integrating the function f in the interval from x to x plus h. So you're integrating your f in an interval of length h, and you are dividing by the length of the interval. You're taking 1 over h. Okay, so if you want to understand it like this, you're just averaging your function f over this interval from x to x plus h. So your function is here. You're just taking an average, meaning you're integrating the function and dividing by the length of the interval. So in some words, you're taking the average value of the function in that interval. If your function is continuous, you may expect when h goes to 0, you go back to the value of the function at the point x. Okay, but what happens if your function f is not continuous? If it's just, say, an integrable function, okay, then we have seen many crazy examples of integrable functions that are not necessarily bounded and so on. So these averages might be very crazy. But you would still like to know something of the convergence of these averages when your when your h goes to 0. Okay, and this brings us to the study of what we call maximal operators. Okay, whenever you want, generally speaking, in analysis, to study some pointwise convergence results, you are naturally led to consider these so-called maximal operators and try to prove bounds for these. Okay, so this is going to be the following object. So let f Now let's move to the whole Euclidean space. So let f be a function which is L1 of Rd. So it's an integrable function on Rd. Okay. We define the Hardy-Littlewood maximal operator M as follows. So I will construct a new function, which I'm going to call M of f. That's called the maximal function. M of x at the point x will be the following. You will take integrals of modulus of f of y dy over balls. B is a ball. And you are going to divide by the measure of the ball. So you are going to take averages of your function f over balls. Then you're going to take the supremum over all balls that contain your point x. And this is your definition. Okay. So if you give me a point x, the maximal function mf at the point x is just the supremum over the averages of the absolute value of f over all possible balls that contain my point x. Okay. So here, if your point x is right here, somewhere in the space, you're allowed to take maybe a big ball, you're allowed to take a small ball, whatever you want. The balls don't have to be centered in x, they just have to contain your point x. Okay? And I note to you, let's observe that you're taking the absolute value here of the function inside the integral, okay? So this is to start with, this is a non-negative thing, and you have a supremum of some non-negative numbers here. So this is certainly well defined. It could be infinity, there's no problem about that, okay? This is called the Hardy-Littlewood maximal operator. Let's see a little bit. So the first claim that I want to make to you is that the first claim that I want to make to you. So, okay, M here is the Lebesgue measure. Okay, so this is the Lebesgue measure of the ball. The balls that you take could be open or closed, doesn't matter. Okay? They just have to contain your point X. My first claim is that if your function is not the zero function in L1, okay, it's not zero almost everywhere. If your L1 norm is strictly positive, my claim to you is that then this maximal function f of x is bigger or equal than the L1 norm of x, say a certain constant, divided by x to the d, when x is large. Okay. D is always the dimension, okay? Why is that the case? Let's do this, okay. So suppose you have a function f here living in the Euclidean space Rd. Okay. And I'm telling you that the function has norm strictly positive. It's not the zero function. Okay. So then there must be a big ball centered at the origin, must be a big ball centered at the origin such that the L1 norm of f, characteristic this big ball here of radius r, is already, I don't know, half of the norm of the function, okay? Your function is integrable, just take a big ball around the origin such that the mass at that ball, I mean the L1 norm inside here, is already half of the whole mass. That's good. Now you go and you take a point far, far away in the galaxy, X. Okay? Well, you want to consider averages over balls that contain your point X, don't you? Okay. But if you take balls very close to X, maybe the function is just 0 there. I mean, and you're not picking up any mass. But there is one way for you to pick up some mass. You know that this R is fixed, and this little ball of radius R has some mass in it. So if you're given a point X far away, you are allowed to choose a ball that takes your point X, but goes all the way here in the space and picks up this big ball at the origin. Okay. In other words, you can take a ball, say, you can take a ball B of center in the origin, not center in the origin, I'm sorry. You can take a ball B of radius, let's say, absolute value of X plus this little r. So what you did is like, you have absolute value of X here, and you threw a little bit of r to the other side. So if you take this ball here, this big ball is not radius, but it's maybe a diameter, it doesn't matter. Just take a big ball that contains this little ball there. Okay. But then you are okay, right? Because then when you take 1 over the measure of this ball B, the integral of f in this ball B, okay. Let me erase here. The maximal function of x at the point x is the supremum over the averages of all balls. In particular, it's bigger or equal than this particular ball. But in this particular ball, what you get is, well, the Lebesgue measure of the ball is essentially the radius or the diameter raised to the d. Okay, times a constant maybe. And the integral of f over this ball, you know, this is at least half of the, you should do this. This is bigger or equal, and this times the integral of f over this little ball br that you took initially, right? And this is going to be 1 over a dimensional constant, say x plus r to the d, times the L1 norm of f over 2, because you chose this little ball in the beginning to have at least half of the mass. But there you have it, you know, since your x is large and r is fixed, so r is fixed and x goes to infinity here. Of course, this is bigger or equal than, say, a certain constant, L1 norm of f over modulus of x to the d. You know? Because this is what's dominating the denominator here, x to the d. Okay, so for this I just used that x plus r is bigger or equal than x over 2, for example. If x is bigger or equal than r. So then 1 over x plus r to the d is less than or equal than 2 over x to the d. Okay, so if you just plug in this right here, you deduce this thing. Okay, so we really have, if your function is not 0, you just prove that the maximal function cannot decay very fast. Okay, This is going to be bigger or equal than a certain dimensional constant over x to the d. In particular, your maximal function will not be in L1, will not be integrable. Okay, so this is as x goes to infinity. We have seen that in dimension d, the function 1 over x to the d is not integrable. Okay, so this any function that is, of course, bigger or equal than this cannot be integrable because 1 over x to the d does not integrate at infinity. Okay, so you started with your function, you started with the function in L1, you construct this maximal function, which is supposed to be something that lies above your function. So this is bigger, and it does not fall in L1. So it's you're getting something here which is bigger. And the point is that I want to make to you is that this is not so much bigger. By the way, if you have any questions, feel free to interrupt me at any time, okay? Let's see. So we have seen this space.
I have a question.
Go ahead.
What's CD?
What's what?
CD, C subscript D.
D is a constant. CD is a constant that may depend on the dimension. Okay? CD is just a dimensional constant. Here, I had some choose floating around. I had some CD that maybe depended on the volume of the unit sphere, you know, the volume of the unit ball. And the CD, it's not the same from line to line. Every time I skip a line, I might be changing my CD. The C and CD in this lecture is just a constant that depends only on the dimension. Okay. Okay, so we have seen this space that I called to you L1 weak space. This was a space that contained L1, was a little bit bigger. Okay. And this is the space of functions, f such that there exists a constant c bigger than 0 for which the estimate holds. The measure of the set where f is bigger than, say, lambda loses to c over lambda. Okay. So this is the space we call L1 weak. Okay. We have seen that so if f belongs to L1, so if a function is integrable, we have this Chebyshev's inequality that says that the measure of the set where f of x is bigger than lambda in absolute value is less than the norm of f over lambda, right? So if a function is in L1, this thing here above works with the constant c being the L1 norm of f. Okay, but in general, you don't need to have the function in L1 to have this inequality of the L1 weak space, right? And a prototype of the function that belongs to L1 weak and does not belong to L1 is a function of the decay, say 1 over x to the d. Okay? So this function 1 over x to the d is exactly a function that is not in L1, but it's in L1 weak. Okay. So L1 weak is a larger space than L1. We have seen, you have done many exercises on this, So this is exactly the decay that my maximal function is having at infinity. Well, at least that decay, okay? So I want to show to you this. I want to show exactly that this function belongs, the maximal function belongs to this space L1 weak. And I want to show to you the following bound. So the main theorem of the class today, this is called L1 weak estimate for the maximal function M. Okay, so the L1 weak estimate for the Hardy-Littlewood maximal operator is the following. Okay, so if F belongs to L1 of RD, there exists a universal constant C, which may depend on the dimension, CD, such that the measure of the set where the maximal function is bigger than lambda loses to the C times the L1 norm of F over lambda for all lambda bigger than 0. Okay. So this is a way of saying that the Hardy-Littlewood maximal operator M maps L1 into L1 weak boundedly, you know. So the L1 weak norm that appears here is it's not exactly a norm, but is bounded by the L1 norm of F on the right-hand side, okay, in this sense. And so this is the first theorem of the class today. We will see what we can do with this. Let me, okay. Let me, so some of the results in analysis, which may seem hard, they rely actually in some very interesting and basic geometric facts, and this is one of them. So the proof of this result, and we will see how important, this is a very important result in analysis. We're going to prove in this lecture today, the Lebesgue differentiation theorem, which will use this estimate. So this relies on a very interesting geometric insight called the Vitalik covering lemma. Vitalik covering lemma is the following. You know, it's a very basic lemma. We're going to prove this first. So let B, so let's call italic B here, say B1, B2. Give me a collection of balls, a finite collection of balls. The balls could be closed or open. You don't care. And we are in RD, okay? Give me a finite collection of balls in RD. So the balls may be intersecting, you don't know. And this is a finite number, but could be many, many balls. The lemma states that then there exists a disjoint subcollection of balls. So you gave me a collection. I claim that there is always a disjoint subcollection of those balls. Let's call BI1, BI2, up to BIK of this collection B, such that these disjoint balls cover a considerable part of the whole set, meaning that the measure of the unions of all the BLs, L's from 1 to n, the measure of the union of all balls loses to a certain number, C, times the measure of only these balls here, BIK. BI. Maybe I should write it like this. Maybe I should write it like this. The sum of the measures of this Bij, j from 1 to k, is bigger or equal than a certain universal constant times the measure of the unions of all the balls. Okay. Okay, so what I'm trying to say is that if you give me a bunch of balls, of different sizes, of different and different positions in the space, you give me any collection of balls, finite number of balls. Inside this crazy collection that you give to me, I can always find some disjoint balls such that the sums of the volumes of these disjoint balls is bigger or equal than a certain universal amount of universal fraction of the whole volume covered by the balls. So let's say 1%. It's at least 1% of the whole volume, or 2%, or 10%. Let's see what this number is. But the point is that this constant C here is just a constant that depends on the dimension, but it's universal. It doesn't depend on the covering of the balls, you know? It's just a number. For any covering, you can get me a disjoint subcollection of balls that cover at least 1% of the whole volume. The proof is very simple. It's based on an interactive argument. So let me do the following definition. So if B is a ball, let me denote by B star the ball. Let's say if my ball B has center X and radius R. So B star is just going to be the ball of center X and radius 3R. Okay, so this is concentric with 3 times the radius. Okay, so if B is a ball, B star is going to be the ball with the same center and radius 3 times the radius of the original ball. Okay. This is R, this is supposed to be 3R. Okay, so you start with your collection. You have a collection, a big collection of balls, B1, B2, Bn, but it's finite. So what you do first is that, so step 1, what you do is you choose, of course, you choose the largest ball. Choose a ball with the largest radius. Okay, I shouldn't say the largest ball because there may be many balls with the same radius. So I can just say choose a largest ball. Choose one ball with the maximum radius in your collection. Just call it B BI1. Now what you do is that you delete from the collection delete this ball BI1 that you chose and all the balls that intersect BI1 star. Okay, so you chose a ball with the largest possible radius. So this is BI1, this is BI1 star. So, and there may be other balls in your collection that are intersecting this BI1 star. So you will remove this ball that you already chose, BI1, and you also remove all the balls in your collection that intersect this BI1 star. The big ones and the small ones. If they intersect, you remove them. So you are left with a collection, let's say B star, B prime, okay? So after removing these balls, you're left with a collection of balls B prime. And then you repeat the process. Repeat the process. Choose the largest ball in the collection that you have. Choose this ball, call it B, okay? You choose the largest ball, call it BI2, which by construction is not touching this BI1 star, okay? So maybe your ball BI2 is right here. And you will delete all the balls in your collection B prime that you have that touch BI2 star, okay? And so on. Okay. Eventually, you will finish because the original number of balls is finite, and at every step you pick a ball. You pick one ball to choose, right? So the process will finish. Okay, when it finishes, you will have chosen the balls BI1, BI2, BIN, BIK, N is your original number. Okay. Okay. But it's important to notice the picture here, right? By construction, this ball's BI2, for example, was not touching the ball BI1 star. Okay. So let's see. Now let's see what's going on here. The measure of the unions of all balls, 1 to n. So since my process finished, you know what? Maybe I need to do no, I have to do something slightly different. It's not this. So let's go back. Let me go back to the interactive argument. Let me say this. Let's go back. Choose the largest ball, call it BI1. Delete from the collections the ball BI1 and now the balls that intersect. Aha. So okay, so I made a mistake here. I will remove all the balls that intersect BI1, not BI1 star, okay? So my picture is not going to be like this. I want to do it again. Let me do it again. Okay. So I will choose the largest ball, BI1. That's it. And I will remove all the balls in the collection that intersect this ball BI1. Okay. I will remove all of them. The observation is that since the ball that you took has the largest radius at that time, all the balls that intersect them will be contained in the ball with the same center and radius 3 times. This is what we call BI1 star. So all the balls that you are removing, all the balls that intersect this ball BI1 are contained, entirely contained in the ball BI1 star. Okay. This is due to the fact that the ball BI1 has the largest radius. Okay, then you are okay. Then you repeat the process. You choose the largest ball that is left, call it BI2. BI2 is not intersecting BI1. It could be intersecting, it could be inside BI1 star. Okay, so it could be right here. That's fine. BI2. And then you remove all the balls that intersect this BI2. Of course, all the balls, since BI2 is the largest one at that step, all the balls that intersect it will be contained in the ball with the same center as BI2 in radius 3 times. And you keep doing this. At the end, the process will finish. All the balls, you have chosen a collection of balls that you call BI1, BI2, BIK. Now, take a look at the following chain of computations. The measure of the union of the BLs, of the union of all the balls, is less than or equal than the sum. Maybe I should put it like this. Then the measure of the unions, now J from 1 to K, of the Bij star. Okay. Because all the balls in your collection will be inside one of these Bij's star. Do you agree with that? Okay. If you have a ball that is not in any of these Bij's star entirely contained, if the ball is outside, then it's not touching any of the balls that you chose, and hence your process has not yet stopped. Okay, just argue by contradiction. If there is a ball BL that is not entirely contained in any of these, that it's a little piece out, then the process is not over yet.
But
okay.
these balls are not disjoint, right?
These balls are not disjoint. These balls Bij stars are definitely not disjoint, but this loses to, okay, I'm sorry. Right here. These balls are not disjoint, but certainly the measure of the union loses to the sum of the measures, Bij stars. And now the measure of Bij star is just 3 to the D, sum from 1 to K of the measures of Bij's, right? If you have the radius that is 3 times the radius of the other ball, the Lebesgue measure will be multiplied by 3 raised to the dimension, 3 to the D. Well, and here it is. And now the balls Bij that you constructed, these balls are disjoint. These here are disjoint by construction, right? You chose the ball Bi1, you deleted all the balls that touched this ball. So the ball Bi2 by construction is not touching Bi1. You deleted all the balls that touch this Bi2, And then the BI3 is chosen not to touch BI2 or BI1, and then so on. So these are disjoint. And this is the inequality that you wanted. This implies that the sum of these BIJs that you selected here is bigger or equal than 3 to the minus D. So you see, the constant is very small. We proved this result with the constant 3 to the minus the dimension, which is very small, but we don't care. We just care is that this is a universal number. Okay, so for any collection of balls, there will always be a subcollection that covers a universal portion. This universal portion is 3 to the minus D of the whole volume. 0.0001%, but we don't care, as you will see, okay? So this concludes the proof. Well, again, the proof is very simple. You just pick the largest ball. Since you want to construct a set, disjoint collections of balls, you delete all the balls that touch this one that you chose, and you repeat the process. Pick the largest ball, delete all the balls that touch it, pick the largest ball, delete all the balls that touch it, and then keep going. With this, I mean, this is the first idea that one should have, but this idea, in fact, actually works. It's just a matter of analyzing it. Okay? So this is very interesting. Now let's go back to the proof of our theorem. Let's prove our theorem 1. Remember, the theorem, we had a function f in L1, and we wanted to prove that the set, the measure of the set, or the maximal function, is bigger than lambda, would lose to this, right? Well, okay. So let's call this set, this is what we wanted to prove. So let's call it, let E lambda be this set here. This is X belonging to RD, such that MF of X is bigger than lambda. Okay. So the first observation that I make about this set is that this is, you could ask me, well, Emmanuel, why is this function MF a measurable function? Why is this set measurable to start with? I actually claim to you that this set is actually open. This is an exercise for you to verify that the set is open, in the sense that if a point X belongs to this set, meaning that the maximal function at X will be bigger than lambda, strictly bigger, since the maximal function is a supremum of things, you will be able to find a ball around X on which the average of this function is bigger than lambda. And then, well, this is the ball, this is the point X. And then you can just move X a little bit and still consider the same ball, or maybe just move the ball a little bit. And this won't affect the result if you just move your ball a little bit. In the neighborhood of X. Okay. You have shown this, you have seen this exercise that if a function is integrable, then for any given epsilon, there is a delta such that if the measure of the set is less than delta, the integral over the set of the function is less than epsilon. We have to use that. Anyway, this set is actually open. And here's the thing, you know, so for each X belonging to the set E lambda, there exists a ball, let's call it Bx, such that Well, the average, well, x belongs to the ball bx, and the average of your function over this ball bx is bigger than lambda. This is by definition. Okay, so every point x is covered by a ball. What you do is you let k contained in E lambda be a compact set. Okay, so you have here your E lambda, you have here your k, which is compact inside. So every point in E lambda, there's a little ball here. We can choose this ball open. So this is an open ball. This is an open ball Bx. Verifies this. Okay. If you integrate a function over a closed ball or an open ball, it doesn't make a difference, okay? This is an open ball such that the average over this ball is going to be bigger than lambda. Okay, so now you take a compact set inside your E lambda. So every point is covered by a ball. And let's now from now on, it's just a sequence of natural steps. So what do you do if you have a covering of a compact set with open balls? Well, it's the only thing that you can do. So you take a finite covering of K. Say, cover this K byte balls B1, B2, up to Bn. Now we are going to use the previous lemma. You have a finite collection of balls, B1, B2, Bn. So by this Vitalik covering lemma, choose BI1, BI2, BIK, disjoint, such that sums of the measure of this Bij's, 1 to k, was bigger than or equal than 3 to the minus d, the measure of the unions of the BLs, right? Now let's see, let's rewrite this thing. Now observe the following. The measure of K certainly loses to the measure of the union of BLs because this BLs covered K. Now I use this inequality right here. The measure of the unions of BLs loses to 3 to the D. I'm moving the 3 to the D to the other side. Sums of the measures of Bij's, J from 1 to K. Okay. Now I have to go back to my definition of the set right here on top. I don't know if you can see me writing. You have to use this right here. Okay. So in each ball, recall that, so let me fix this for a minute. In each ball, remember that 1 over the measure of this ball, integral of f over this ball, Bij, was bigger than lambda. Okay. So I'm going to go from this. It's going to be less than or equal then. So I'm using this. 3 to the d, the sum from J1 to K. In each of these balls, if I move lambda to this side, integral of f, Bij, this will be bigger than the measure of this ball, Bij. So the measure of the ball will lose to the 1 over lambda, integral of f over Bij. And here is the important, why is it important to have the balls disjoint? Because the sum over the integral of f over these balls loses to the integral of f over the whole set, say over Rd. You don't care. Okay. Here you just use that the balls are disjoint. You have shown, what you have shown is that you have shown that the measure of K of this compact set was less than or equal than 3 to the D over lambda times the L1 norm of F, which was finite. Now, but since K contained in E lambda is an arbitrary compact set, we know from the regularity properties of the Lebesgue measure that the measure of E lambda is the supremum of the measures of the compact sets inside, right? So this implies that the measure of E lambda itself would have to be less than this 3 to the D over lambda F1. This is what we wanted to prove, okay? Okay.
I have a question.
Go ahead.
Okay. Why from okay, you said the BIJs are disjoint and then the integral became over the entire RD. Why? The second line to the third line on the current page.
I have a sum here, right? Sum of the
Yes.
sum from J1 to K of the integrals of F over this balls Bij. And I just use the fact that this is less than the integral of F in RD.
Okay.
It's just because this is the sum of the integral of F over disjoint sets. This is just the what is this doing? This is just the integral of F over the union of Bij's, right? Okay. Okay, with this in hand, so now we have proved this Vitalik covering lemma, which essentially says that if I give you any collection of balls in the Euclidean space, I can find a disjoint subcollection that covers a portion of the union, and this portion is universal. It depends just on the dimension. With this basic covering lemma, we use to prove this L1 weak type estimate for the Hardy-Littlewood maximal operator, in the sense that if F is in L1, then the measure of the super level set for the maximal function is bounded by L1 norm of F over lambda times a universal constant. And now we are able to prove the main theorem of today. This is called Lebesgue's differentiation theorem. Okay. And the theorem is the following. If a function f is locally integrable, then the limit when the measure of the ball goes to 0, point is inside the ball, of the averages goes back to the value of the function for almost every x RD. Okay. Look at what this statement is telling us. This is what we may think of as the fundamental theorem of calculus for integrable functions, in the sense that the averages, if you take any integrable function f, this could be a crazy function, but if you fix this integrable function and you take averages of this function around each point with balls that contain that points. But if you make these averages, if you make averages over balls that shrink to 0, so the limit of these averages will go back to the value of the function at that point for almost every point in RD. Not for all, but for almost all. Okay, this is very important. You cannot get the convergence back everywhere. You can just get the convergence back almost everywhere. Remember, we say that the function is L1 locally integrable. Locally integrable means that this is saying that if you just multiply by the characteristic function of any ball, this is in L1. Okay, it's just a function is locally integrable. A function that is locally integrable doesn't need to be integrable in the whole space. But if you multiply this function by the characteristic function of a ball, then this becomes integrable. Okay, so a function which is constant equal to 1 in the whole space is of course not integrable in the space, but it's locally integrable. Locally integrable means that you can integrate your function over any ball. Or in other words, if you multiply your function by the characteristic function of any ball, this is integrable in the whole space. Okay, this is just a note. Okay. So it's a pity that we didn't have the board today, because this is actually one of my favorite classes in this course. And this is one of my favorite theorems in this course. You know, this is called the Lebesgue differentiation theorem, saying that the limit of the averages, if you make the averages over balls and shrink the averages, the balls to 0, this limiting of the averages will go back to the value of the original function almost everywhere, if your function is integrable. With what we have in hand, the proof is very interesting. So proof, let's see how we connect the pieces together. Okay, so since this is a local result, since this is a local result, I mean, you're fixing a point and you want to know the averages over balls shrinking, right? So you may just work with f times the characteristic function of a big ball, replacing f, right? Okay, so in other words, if you are here around a point and you want to understand what happens here, you can just you know, look just at the big ball around that point. You know, let's say if this is the origin, just take a big ball and consider f times the characteristic function of this ball, replacing your original f. So you don't care if what your function does outside this ball. You won't take big averages anyway. Okay, so this is just to say, well, in other words, you may assume that your f is actually nil 1. Let's assume that my function is integrable in the whole space. Okay. Let me assume that my function is integrable in the whole space. Okay. We shall prove the following. We shall prove a slightly stronger statement. Remember, my statement is to verify that this integral of f of y dy over a ball, and then I divide by the volume of the ball to show that this goes to f of x, right? When I shrink my balls to 0, and this goes to f of x almost everywhere. Of course, f of x, this is an average. Remember, always have in mind that we are taking averages. So I can just write f of x as the integral of f of x dy over a ball, measure of the ball. This is what I want to prove. Look, in this integral, I'm integrating over a variable y, and I'm fixing this f of x. So f of x is just a constant here. Goes out of the integral. Then I'm integrating the function 1 over the ball, dividing by the measure of the ball. This is 1. Okay, so in essence, what I want to show is that this thing here goes to 0 if I subtract. So this is what I want to show, that the that the integral over balls of f of y minus f of x goes to 0 when I shrink my balls to 0. So we shall prove that 1 over, shall prove the following. Shall prove actually that the limit when the balls shrink to 0, my point is inside the ball, of 1 over the measure of the ball, integral over the ball of f of y minus f of x in absolute value, y. This is it. Okay, so if I prove this with the absolute value, of course, the integral without the absolute value inside loses in modulus to this one and will always also go to 0. Okay, so this is what I want to show. Okay. Okay. I want to show that this limit is 0 for almost every x in RD. Okay, so let's see. Let us consider the points x. Let me consider only the points x such that f of x is finite. Okay. So this is almost everywhere, right? Since my function is integrable, the value of f at the point x is finite almost everywhere. Okay, so point x is finite. Okay. So in order to prove this statement star that I'm marking here, so for each lambda bigger than 0, let us define the set E lambda to be the set of points x in RD such that the lim sup, okay, it's part of my statement to actually prove that this limit exists. So in principle, I don't know that this limit here in star exists. We shall prove that. So let me, for any lambda bigger than 0, let me define the set E lambda, which is a collection of points in RD, such that the lim sup, when the balls go to 0, and x is inside the ball of this thing, 1 over measure of the ball, integral of f of y minus f of x dy over the ball with the absolute value is bigger than 2 lambda. So let me call this the set E lambda. Okay. So it suffices to prove that the measure of the set E lambda is 0 for all lambda, right? So remember, I want to show that this lim of these averages is 0 almost everywhere, okay? So if it's not 0 almost everywhere, then this lim sup will be positive on a set of positive measure for some lambda, right? So if I define this E lambda being, well, the set where the lim sup is bigger than 2 lambda, I have to show that the measure of all of these sets is 0 for all the lambdas. To do this, okay, so we proceed as follows. Given epsilon bigger than 0, let us choose a function g, let's say continuous with compact support in RD. Is a function which is continuous with compact support, such that we have already seen that the functions that are continuous of compact support are dense in L1. So if I gave you f, I can choose a g continuous of compact support such that this is less than or equal than epsilon. Okay. Now, observe the following. Observe that 1 over measure of b, integral of b of modulus of f of y minus f of x. We go to the usual splitting in 3 arguments, right? So I'm going to split this into 3. I'm going to put my g into play here. So this is less than or equal than 1 over measure of b. And then I'm going to put f of y minus g of y plus 1 over measure of b, g of y minus g of x, dy, plus 1 over measure of b, integral of b, g of x minus f of x, dy. Okay. With this in mind, hence, let me compute now the lim sup when the measure of the ball goes to 0 and the point x is in the ball. This thing here. So the lim sup of this thing, of course, loses to the sum of the lim sups of these 3 other things. Okay. So first of all, this guy is an average of the function f minus g. So this loses to the maximal function of f minus g at the point x. The second one, this lim sup of g of y minus g of x is 0 because g is a continuous function. So if g is a continuous function, when you take these averages and shrink the balls to 0, this will converge to 0. And the third one, you have just g of x minus f of x being a fixed value here. And you're taking the average over a ball, integrating in the variable y, which is another variable. So you really get here g of x minus f of x. Okay. So you get this very nice looking inequality. Okay. Now, remember, the set E lambda was the set where this first guy here, star, blah, 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 the set where star was bigger than 2 lambda. But you have seen that star is smaller than a sum of 2 things, you know? So if I define, let me define the set f lambda as the set of x in Rd, such that m of f minus g of x is bigger than lambda. And let me define the set g lambda of the points x in Rd such that modulus of g of x minus f of x is bigger than lambda, my claim, which is a very easy claim, is that the set E lambda, which we originally defined, is just contained in the F lambda union this G lambda, right? So, and this is just because of this inequality that it's in your screen in red. Okay. If you look at this inequality in red, the left-hand side is bigger than 2 lambda. The right-hand side, one of the guys must be bigger than lambda. Okay. So if a point X belongs to E lambda in the sense, if a point X is such that the left-hand side is bigger than 2 lambda, the point X must be such that one of the two guys on the right is bigger than lambda. Good. But then, okay, so this claim clearly implies that the measure of E lambda is then less than or equal than the measure of F lambda plus the measure of G lambda. Now, you use what you know for measuring these two sets. So the first one, by the L1 weak estimate for the Hardy-Littlewood maximal function that we proved in the first theorem today, you know that this measure of the set F lambda, which is the set where the maximal function of somebody is bigger than lambda, is less than or equal. You know that this is less than or equal to a universal constant, the L1 norm of the function. The function here is F minus G over lambda. And the measure of the set G lambda, well, G lambda is the measure of a set where a certain function is bigger than lambda. You can use Chebyshev's inequality here. So this is less than or equal than the L1 norm of this function, which is F minus G over lambda. Okay, so hence, what you get is measure of E lambda less than or equal than measure of F lambda plus measure of G lambda. But this is less than or equal than, well, you have, we can factor out C over lambda plus 1 over lambda times this F minus G1. This was less than or equal than C over lambda minus plus 1 over lambda times epsilon. Remember, this function G was chosen such that the L1 norm of F minus G was less than epsilon. Lambda is fixed. Since this epsilon bigger than 0 was any number, we get the measure of this set. Okay, so here's the proof. This completes the proof. This is one of my favorite theorems in this course, the Lebesgue differentiation theorem. So now you know that every time that you get an integrable function or a locally integrable function, okay, the function might be as crazy as you want, but if you take averages over balls and the balls shrink to 0, this will have a limit almost everywhere. So for almost all points, the limits of the averages will converge back to the value of the function at that point. Okay, this is an example of a pointwise convergence result, where we needed to go and study this maximal operator associated to it and prove some sort of boundedness for this maximal operator associated to it. And you saw in the proof here how the boundedness of the M appears, okay, in this step here. So this is crucial where the boundedness of the M appears in this step. So we used this boundedness of the maximal operator to prove the pointwise convergence result. And we also used the fact that there was a dense subclass of functions for which the result holds. Namely, if your function is continuous, then this convergence of the averages to the value of the function actually happens everywhere. So this is a general mechanism in analysis. Sometimes when you want to prove a convergence result, one strategy is exactly this. You have a dense subclass for which your result holds, and you have a certain boundedness for the maximal operator associated to your convergence problem. Okay. Okay. I think I'm going to send you later, maybe later today or this week, some notes about this so you can read more. The next step in our conversation would be to talk about functions of bounded variation and absolutely continuous functions. But I don't think I will start today since we're just 5 minutes left. So I will stop here today, and we are going to continue our conversation next Thursday, okay? Do you guys have any questions?